The second half of the set questions you can then do after learning this lesson. Gentlemen, could we consider initial and final? We are going to have a cart, call it M1, and it is travelling with an initial speed, call it U1. We now have to be very confident with using all these different notations. It's going to collide with a stationary mass. Okay? So initial, we could also say before. Final, we could say after. Doesn't matter what you use. Now, gentlemen, if this was two equally sized masses, then normally what would occur is like a billiard ball colliding. The first mass would remain stationary and it would impart all of its momentum into the second mass, like a cue ball hitting a ball straight on. All of the momentum is imparted. But that doesn't necessarily occur. If they were different masses, it's not going to occur like that. So let's just suppose that after the collision, they're both moving forward. Okay? Beneath, we are going to write a few things. We could say that the sum of our initial momentum is P1 initial plus P2 initial. I could write that as M1U1 plus M2U2. Okay? So this is sum of initial momentum. We got two objects. It just happens in this scenario that one was stationary, but don't draw that because the different scenarios are going to have different velocities. All right. In this scenario, the initial momentum is contained solely due to the motion of M1. Afterwards, we could then write the sum of final momentum. We can write it as such. Sum of P final equals P1 final plus P2 final. And remember, these are vectors. We could go through and put little hats on every single one. Don't have to, but just remember, positives and negatives. We have to assign a convention. Right is positive, left is negative. North is positive, south is negative. We could write that as M1V1 plus M2V2. Okay? Now, during collision, so I'll write it here, M1, M2. This is now the in-between. So we had before, we had after. While they are colliding, Newton's third law is going to come in here and give us a nice equation. We have our action force, which acts upon M2 and accelerates it to the right. We have a reaction force, equal and opposite. Where am I going to write it? Equal and opposite, it acts on M1 and it accelerates it left, meaning it slows it down. We are going to use Newton's third law here. We would say that FA equals negative FR. Can I change? Sorry, let me change that. Doesn't matter, you're just going to have ones. FR, right, reaction, yep, FR equals negative FA. Now let's throw in Newton's second law, that M1A1 equals negative M2A2. So all I've done is substitute in force equals mass times acceleration. Now let's throw in the acceleration equation. I'm going to write M1 outside of V1 take U1 over T1 equals negative M2 outside of V2 take U2 over T2. Okay? Happy so far? What? They are. See, I've just gone to red because I was going to put a little asterisk here and say that the time that mass 2 is touching mass 1 is the same as the time of mass 1 touching mass 2. And so we can cancel them out. We'll go M1 outside of V1 take U1 equals negative M2 outside of V2 take U2. Okay? What I'm going to do here is put all of my U's on one side. Let's expand first. So negative M1 U1 plus M1 V1 equals negative M2 V2. Oh, did I stuff up? No. Why did I put U first? Oh, I was going to put U first. Plus M2 U2. Damn it, I was hoping that this would come out nicely. You can see, if you put the U's on the right-hand side, they're all positive. And if you put the V's on the left-hand side, they'll all be positive. So I'm just simply going to go M1U1 plus M2U2 equals M1V1 plus M2V2. This is called the conservation of momentum. It says that in any collision, the sum of your initial momentum equals the sum of your final momentum. That the momentum can be transferred from one object to another, but the sum of the momentum is always the same. Okay? So in a collision, one object might slow down. It must be because the other object is speeding up. The momentum that the object slowing down loses must be the momentum that the speeding object gains, such that the changes in the momentum sum to zero. Okay? If we go back to here, I'm just going to put a big fat equals sign in our initial statements, that the sum of the initial must equal the sum of the final, that sigma p initial equals sigma p final, that M1U1 plus M2U2 equals M1V1 plus M2V2. Okay? It's the same. So, put that in a box and highlight it. Now, unfortunately, while I'm writing this, part of me is thinking, I'm pretty sure this is in your data sheet, but it's only the bottom box that's in your data sheet, which is a bit of a bummer. You need to sort of remember and regurgitate M1U1 plus M2U2 equals blah, 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 blah. So let's just have a quick look. Momentum. There it is. Look, that's all you got. Okay? All you got is that. So, ooh, hello. You need to be able to, it's interesting. Fun. You need to be able to expand that equation into M1U1 plus M2U2. It rolls off the tongue quite nicely. The two masses, U's on the left-hand side, V is on the right-hand side. Cool? All right. Let's jump into some scenarios. Now, I have got about 6 or 7 or 8 scenarios. I'll do maybe 2. You guys can then do the remaining. However, gentlemen, every single question, I would like you to assign your scenario convention. Okay? So, this agrees. M1 is traveling that way. M2 is stationary. Now, this one's a really easy one. This is the billiard ball example, where all of the momentum is in the first mass and all of the momentum is transferred to the second mass. We are told that because we're told V1 is stationary. However, let's write everything down. sum of momentum initial equals sum of momentum final. M1U1 plus M2U2 equals M1V1 plus M2V2. I'm going to copy and paste that because we're going to write that for every single goddamn scenario. Okay? All right. Now, before we throw everything in, you could rearrange this equation for your unknown now, or you could throw the values in and then rearrange. It's entirely up to you. But first off, we can get rid of V1 because it equals 0, and we can get rid of U2 because it equals 0. It becomes a really, really easy equation. If I was to rearrange M2V2 equals M1U1, okay. Now they're the same mass, and this has to occur. If they're the same mass, it's 2 by plus 4 over 2 equals plus 4 meters per second right. 4.00. I'll just tidy this up while you copy.
Does that assume it's perfectly elastic?
Absolutely, yes.
Will we receive like one that is friction, or say
well, yes.
Rebound?
The only way to determine whether it's elastic or inelastic is to consider energy. So we'll look at kinetic energy next week, and then we'll come back and look at this scenario. Basically, there's one more way to look at it, is to say, how much kinetic energy was there at the start? Oh, it's a half mv squared. There's 16 joules at the start. How much energy is at the end? Oh, there's 16 joules. Energy was conserved as well. We call that elastic. But for now, we'll just ignore elastic and inelastic. All right. Now, gentlemen, I'll just do that. But before we start, let's assign our conventions. So, a 3 kilogram mass, M1 equals 3. It's traveling initially plus 2. It collides with M2, that's 6 kilos, which is initially stationary. The 3 kilo mass recoils. That means backwards. So V1 is then negative 1.6. And then the question is, well, I didn't state the question, but what is V2? So this can occur. And in tomorrow's lesson, I'm going to set up a few scenarios on a dynamics track with photo gates, and we can, in the class, show that momentum is conserved. This is a small mass hitting a big mass, and then they bounce away from each other, okay, which does occur. If you have a small object and a big object like this, and it goes like this, you can actually get the small object recoiling. So be aware. The forces during the collision are equal and opposite, but since one is less massive, its acceleration must be more. And that's why it changes direction. All right, so the acceleration of the smaller mass is greater, and that's why we see it not only stopping, but changing direction. The larger mass, its acceleration is less. So, can we cancel out any of these terms? Good, thank you. Shall we now, let's be careful here, gentlemen, because we're going to have subtractions and directions. Julian Cam, what did I just say? Far out, that's good. You can have two conversations at once. That's a very impressive skill. M2V2 equals M1U1 minus M1V1. I've just rearranged for M2V2 on its own, and then I'll divide both sides by M2. And so V2 equals, now, let's be careful here. This is where students make mistakes. They forget the direction of stuff. It's the same damn thing, minus 1.6 over 6. Okay? So I will just color code a couple of things. That is the direction. So please, I say this every year and I highlight it and I put exclamation marks, but 7 of you will forget that negative in the test. And 7 of you will get 2 out of 3 or 3 out of 4. Okay? So I'm sorry, but that's just a fact. Outspits your calculator plus 1.8. Okay. Now have a think. This is travelling right, yes? Yes? Yes, okay. Mass 2, mass 1, small mass, travelling right. Would it make sense that this guy is travelling right? Yes. If it did this, momentum would not be conserved. So, if ready, woo, like that. Alex wasn't watching, ready? If it did this, momentum is not conserved. We're violating a very fundamental law of physics. If I forgot that positive sign, we might, well, we won't, but 6 and...
You just get a smaller...
you get a smaller value, but I was hoping that it would violate it. Okay. Not today, Satan. All right, just before I set you off to do things, combined and coupling events. I'll just quickly go like that, and I'll put it here for now. Can you get to this page, please? Stop talking. Thank you. This is where these are inelastic. More on that later. It basically means that kinetic energy is not conserved.
So, is elastic spelled with 2 L's or 1?
I don't know.
1.
1 L?
Yeah.
Maybe it's because I named it. What's so funny? Ah! Damn English. It's a silly language. All right, that looks ridiculous. That looks silly. It looks wrong. It looks wrong. You know, some words just look wrong.
Yeah, it looks
It's wrong.
Got that right.
That
Okay.
looks wrong.
All right, gentlemen, could we please just have M1, U1, M2? Again, for now, let's just say that it's stationary for an easy scenario. Now, what I'm going to do is put a little locking mechanism here and a little locking mechanism here, such that like a train carriage coming up and it sort of clinks and it locks in, like a little hitch, a tow hitch. Now, here's the cool thing, gentlemen. We can say that this is our combined mass, and that equals... Why do I hear your droning voice? I'm not like Julian. I can't have 2 conversations at once. Shush. M1 plus M2, the combined mass. And V1 equals V2, which I'm going to call the combined. So our new equation down here, since V1 equals V2 and M1 plus M2 equals MC, I could rewrite my equation like, oh wait, hang on. I want you to write it out again because practice makes perfect, but we're going to write it as either M1 plus M2 sharing VC, or just MCVC.
So you don't need MT.
Well, for this scenario, no. But you could have 2 carriages moving and then they lock in, or even 2 carriages coming together and then they lock and travel off. Now, have a think. If you had 2 perfectly equal masses with equal speeds approaching each other and they lock, it'd be 0. But you would have a negative momentum value and a positive momentum, and they would sum to 0. And so your combined momentum is summing to 0. That, not conserved, you're going to have thousands of joules of kinetic energy, thousands of joules of kinetic energy. Bang! That's where the energy goes. It makes heat and sound, and it might break. That's like car crashes. You have two cars having a head-on collision, and they meet in the middle, right? You go, well, where did the 553,000 joules go? Well, that's the mangled wreck of metal and broken plastic and glass. That's where the energy goes. Heat, sound, friction. You've nearly got 20 minutes, but let's consider an example. We'll do it together, and then I'll let you answer all the other questions. M1 is 0.1 kilograms. Have to convert. Oh, assign my conventions. Doesn't really matter. Maybe it does. It's traveling with a U1. We can solve MC quite quickly. That's just going to be a combined mass of 0.4. The end game is what must the final velocity be. So I'm just going to steal this equation. Forgot my sum values. Again, play it safe. Write everything down. Sum of momentum initial equals sum of momentum final. In this scenario, it's colliding with a stationary mass. Again, it becomes a nice question. You can play with the trickier questions in the last 20 minutes. VC equals your initial momentum divided by your combined mass. So the initial momentum was plus 0.4 over 0.4 equals plus 1. Now, this is not the best question because I've given you a direction in, but it's going to be in the same initial direction as mass 1. In initial okay. So again, new scenario, they now couple together and they travel off a little bit slower than before. So the initial momentum is 0.4, the final momentum is let's do it a bit faster. Initial momentum 0.4, final momentum is 0.4. It's just now the momentum is now acting over a larger amount of inertia, and so it's not traveling as fast. All right, gents, you've got all of those other questions to do. You will be prompted with those words about coupling or combining. So just listen out for the word coupling or combine or stick. Stick together. Think of like you throw an object up and then you fire an arrow. It's going to get lodged into the apple and then they're combined. MC, VC, they have the same velocity. All right, gents, get working, please.